Okay, there are three examples here, two kind of generic math problems, while the third is a word problem that I kind of just summarized. And I wrote some formulas in the upper right in red. Let's look at really quick, like what the heck these are even saying. And then you'll see, understanding the formula, it's really easy to apply in these problems. So the first thing we have y prime, remember prime derivative, right? It's a rate of change. So we're saying it's changing at some k times y, which we call that proportional, right? So the change is at a rate proportional to the size. It means you take the original function y and multiply it by some constant and you get its rate. Now I'm not going to show it in this video, but if we were to solve for y, it's not too hard. We actually see that this function, some new constant c, e to the kt, will satisfy that differential equation. Okay, it might be easier actually if we did the derivative of this, we could see it. The derivative of this, we'd see that it falls into this above. And the last thing I wrote is just another way you may come across this same formula with different variables, because it has a lot to applications with population. So we're saying population at time t, which really, this is function notation, right? P of t really just means y, is equal to p naught. So the p sub 0, we call that p naught. And that just is in place of this c, the constant. And then e to the kt is the same. And then a side note I wrote where y of 0 is p naught. So that means just plug in 0 for t, right? That's what we get for p naught. It's the initial value. Okay, another way of writing, just substitute 0. Okay. So this first one, determine k and then find the solutions of the differential equation. The wording of the question is weird, that find the solutions of, oh, by the way, anytime I write DE, differential equation. Okay, that just means it has its derivative, right? There's its derivative in the equation. All right, well, if we wrote it in the form in the first line up above, I would add the y over 2, and instead of y over 2, I'd just write it 1/2 y, right? That's equivalent to what that's saying. And that's it, we're done. We have k, right? K is 1/2. And then it says to find all the solutions. That is referring to this second line here. If k is 1/2, then all the solutions would be in this form. Y equals c, we don't know. E, and then I'm going to plug in k, 1/2 t. Okay, that's it. Again, the question sounds more confusing than it really is. Get it in the first line form to figure out your k, and then plug in k in the second line. In some problems, we'll actually get c, and that's what we're going to do next. So in the first one, we don't know. C is just left as c. Okay. So looking at the next one, y prime equals 3y. It's already in that form. So just looking at that, I know k is 3. Okay, we're solving this given this initial condition. So if k is 3, I could go to the y equals ce to the 3t. All right. Now I'm going to use the second bit of information here, y of 0 equals 1. I'm going to show you the long way to do it and then show you really what that means next. So if y naught equals y sub 0, y of 0 is 1. That means plug in 0 for t. So right there I'm going to plug in 0. And then I'd get 1 for y. Okay, so the rest stays the same. C e to the 3 times 0. Well, e to the 0 is 1, right? So therefore I just get 1 equals c. But notice it told me y of 0 is 1, right? So I really didn't need to do this, but I did want to verify, you know, it's the first one you're looking at, that is what that means. And that's also given over here. Okay, the y of 0 is p naught, but p naught is c, right? It's just many different ways of seeing this type of differential equation and the formulas we're using. So what do we do? Well, now we have k and we have c, so we just write it up. Y equals, I'm not even, right, we do have a 1 there, c e to the 3t, but we don't really write 1 as a coefficient, right? So it's just y equals e to the 3t. Okay. All right, the last one, I summarized the word problem a bit. It gives us p of t, which it's a population problem in millions, t years after 2015. Okay, so the differential equation, the derivative, the rate of change is 0.01 times the original population, or times the population function, and the initial population at time 0 is 2. Find a formula for p of t. So p of t, right here, is equal to p naught, which is this. Okay, p naught or p of 0 is the same thing. So that's a 2. E to the k, so looking at the first line, what is k? It's this, right? This is like y prime equals k times y. So there's our k, 0.01. So e to the 0.01 t. What is the initial population? Well, that we kind of answered like right here, right? The p of 0. That's 2 million. So 2 million people in 2015. Estimate the population in 2019. Well, 2019 would mean t equals 4, right? Because it says t years after 2015, so t is 4. So therefore, it's really saying what is p of 4? So that's 2e to the 0.01 times 4. And just use a calculator, 2e to the 0.04. You get approximately 2.08 million people population in 2019.